Hello and welcome back to the lecture of Applied Econometrics. We are talking about heteroscedasticity and different tests. So previously we have seen Goldfeld-Quant test, Bruch-Pagan test, Cook-Weisberg test. So now we will talk about another test that's called White's test. Now it is an extension of Bruch-Pagan test, only there are some additional variables that we are going to include here. Let me write it down, White's test. Now, how we do it in case of White's test is that we basically use the same idea as Bruch-Pagan test, where my dependent variable is going to be the error square. But however, my independent variable, I am going to incorporate many other independent variables here. So what I mean by that is, let's say I have all the xi's, and then I have, let's say, all the square of the xi's. So basically, if I have, let's say, education, in my xi, so I'll take another variable which is education square, okay, and then I will have the cross term like xi, xj, all the cross product of different explanatory variables. So essentially the idea is that when I'm trying to understand the variance of the error term and I'm trying to understand its correlation with the explanatory variables, I'm trying to see if it is also correlated with the square of my x term, because I'm not really sure. And as I mentioned previously, this is nothing but a proxy for the variance of the error term. You really never get the original error sort of square of the error, the variance of the error term. So because of that, you need to actually sort of keep yourself open to see if the variance of the error term is actually varying with the square of the explanatory variable or the cross product of the explanatory variable. So that's basically the idea of White's test. And like previously, it again follows a chi-square distribution, where if I get the r square value out of this regression equation that I run, if I use the r square value and the number of observations in the regression, I used, and they actually follow a chi-square distribution again, okay. A chi-square distribution with the degrees of freedom equal to the number of explanatory variables. All right. Now, talking about explanatory variables, so the one particular issue about White's test is that we have too many explanatory variables now. So suppose if we had, let's say, 3 explanatory variables previously, okay, let's say all numerical variables, and for these 3 explanatory variables, so now you have you again have to square the 3 explanatory variables, right? So that means you are basically having 6, and then you have to take cross product. So if 3c2, that is again going to, so if I have x1, x2, x2, x3, and x3, x1. So another 3 variables. So initially, if I had 3 variables, I could have my k, x1, x2, x3, a k equal to 3. But now my k is equal to 9, because I am taking x1, x2, x3, their squares and their cross product terms. So k is equal to 9. So the problem with this is that I am actually consuming a lot of degrees of freedom here. And because of that, White's test is performed, and it is always advisable that you perform the White's test when you have a large number of observations, not a small number of observations. And that is why sometimes you may also find that when you are actually testing for heteroscedasticity, you are getting different results for different tests, and that is because the sample size issue. So you might have a small sample size and you perform the White's test, and you will end up getting a different result. Now, another point you need to remember is that for the dummy variables or the categorical variables, so it really does not matter if you square it or not, because this is just categories. 1 square is 1. So for that cases, you don't have to do the square. So you don't need to square a categorical variable. Okay, so that is basically redundant. So that way you have to sort of keep in mind when you actually perform the White's test. So these are basically the major tests for heteroscedasticity. And in the next lecture, we are going to see what we are going to do if we actually have heteroscedasticity in our data. I mean, what is the remedy? Okay, so we'll see some of the remedial measures in the next lecture. Thank you.